Okay, I think we're ready. Welcome from Berlin, everybody, to this week's edition of our ENLA seminar series. I'm very happy to introduce today's speaker, Martin Gander. Martin is well known for his work in many areas in applied mathematics, for example, domain decomposition methods and preconditioners for iterative methods and geometric integration. And Martin also cares about the historical development of the field. For example, jointly with Gerhard Wanner, he has written the fantastic paper From Euler, Ritz and Galerkin to Modern Computing, which was published in Science Review. Martin is co-author of the books Numerical Analysis of Partial Differential Equations using Maple and MATLAB, jointly written with Felix Kwok and published in SciAm, or by SciAm, and the book Scientific Computing, jointly with Walter Gander and Felix Kwok, and published by Springer. Martin is also very much interested in real-life problems and technology transfer, and he was and currently is involved in numerous industrial collaborations and a wide range of topics also in this area, problems ranging from bacteria identification to noise simulation in vehicles. Today, Martin will talk about a linear algebra approach to time parallelization. And before handing over to him, I want to mention that all participants are welcome to write questions into the Zoom Q&A and into the YouTube chat. These two chats are monitored today by Melina Freitag on Zoom and Stefan Guttel on YouTube. And the questions will be asked during appropriate times in the talk. So, Martin, thanks for giving today's lecture, and please go ahead with your talk.
Thank you, Jörg. It's a great pleasure to give a lecture in this new electronic series. It's the first time that I'm broadcasted like this on YouTube and Zoom at the same time. The title you've seen, I want to talk about the time parallelization. And there are 5 algorithms in my title. There is Parareal, ParaExp, ParaDiag, ParaOpt and ParaStieltjes. So you see this para name has become attached to time parallel algorithms. The first one was Parareal by Maday and collaborators about 20 years ago. ParaExp was a name that Stefan Guttel came up with when he was a postdoc here in Geneva. ParaDiag, there's a family of algorithms that Shulin Wu has been working on a lot. I have been working on this as well. Originally goes also back to Ivo Maday. ParaOpt and ParaStieltjes are 2 more recent algorithms that I will only be able to mention towards the end, but not explain in detail. Most of these algorithms have been developed at the PDE level, and most of the analysis has been done at the PDE level. And that's why I think it's really time to build a bridge to the linear algebra community. There are a few exceptions. Andy Watten's group has contributed in a very important way to these algorithms, which you will see during the talk as well. So this talk will contain basically no PDEs, except at the beginning, I need 2 PDE model problems that I will transform immediately by discretization into linear algebra problems. The first one is a heat equation. It's the first model problem. It's sufficient to consider the heat equation in 1 spatial dimension. So here is a time derivative of u equals this Laplace operator in 1D applied to u, plus some source term on the interval 0, 1. And I immediately discretize this equation. I use a backward Euler scheme in time, which you see here on the left, and the centered finite difference stencil for the Laplacian on the right. And I evaluate also the right-hand side function. The index I is the spatial index, and the index J is the time index here. So you can see it's really an implicit scheme. It's a backward Euler scheme. If I want to write this using matrices, I can introduce the matrix Kj, which has a time part, which comes from this term here. And it has a spatial part, which comes from this Laplacian, which I move to the left-hand side. So there's a minus sign. And then there is an M matrix, which contains the remaining part of the time derivative. And I can write all these equations in space-time at once to get the so-called all-at-once system in space-time, which is written here. So you see, it's a block lower bidiagonal system. And this system is usually solved step by step just by forward substitution. So you get the first approximation at time delta t using the initial condition u0 by inverting a K matrix. Then you insert this in the second line, block line of the system, and you solve with K2 to get the second time point solution, and so on and so on. But we write the system all at once, and we try to solve the system all at once. So this is for the heat equation. Now the second model equation is a transport equation. So here we still have a time derivative of u. We have a spatial derivative, but it's just the first derivative in space. And we also can have a right-hand side. I also consider this in 1D on the interval 0, 1. And I immediately discretize. I also use backward Euler here. And I use a centered finite difference for the spatial derivative. And I introduce matrices. The K matrix, it contains this part from the implicit time derivative. It contains the spatial operator here. And we also have an M matrix for the remaining time derivative term. And I get exactly the same all-at-once system in space-time. So these two problems give the same looking linear algebra problem, but these two problems are very, very different problems physically, and the difference is in the K matrix. It's the K matrix that tells us how the solution behaves of this problem in this example. So PinT algorithms, parallel in time, is usually abbreviated by PinT now. PinT algorithms, they try to solve this system or any system of a similar form in parallel faster than sequentially by forward substitution. So you want to beat the sequential nature of the problem because the problem has an inherent sequential nature. The time evolution is forward in this problem, it's not backward. Now there are two important remarks. The first one is the matrix A is highly non-symmetric. So this is not a standard diffusion type matrix. This is because of the time direction. It's highly non-symmetric. And the matrices that appear inside the K matrices, they can be symmetric or non-symmetric. And I have an example of a symmetric one and an example of a non-symmetric one. Now there's a very important early contribution I would like to mention right at the start here by Horton and Van der Walle, who should really be given credit because they started very, very early on to try to solve such systems in parallel. And they developed multi-grid methods in space-time to solve such systems. And they noticed immediately that if you use standard components, like a point Jacobi or a point Gauss-Seidel relaxation, and just restriction and extension operators like use for a Laplace equation, then the method does not work well. To get a method that works well, you need to change one of the components. Either you can have special restriction and prolongation operators, or you must have special smoothing operations. But with standard components, you cannot get the same performance that you would get for a Laplace type problem. The problems they studied are parabolic equations, so it's like my first model problem, the heat equation, not the transport equation. Then in the PhD thesis of Martin Neumüller in 2013, he developed an algorithm that only uses standard components. And at the beginning, it seemed to Stefan van der Walle that's not possible because he had studied this problem. So the main difference in the algorithm in the thesis of Martin Neumüller is that he uses a block Jacobi smoother and not a point Jacobi smoother. And the blocks are very naturally given by the system. You see, this is a block system. So the block Jacobi smoother, it just inverts K1, K2 up to Kj. This is the Jacobi step. It's a block Jacobi method. Otherwise, all components are standard. You have normal space-time coarsening. With analysis, you can show that you need the damping parameter in block Jacobi, which when it's optimized, it's a half. And the space-time coarsening needs a certain schedule. So you can always do time coarsening, and under a certain condition, you can do space-time coarsening as well. but it's just using standard components. And this algorithm has extremely good scaling properties. You see two tables here for a 3D heat equation that were calculated by Martin Neumüller. The first table shows weak scaling results. So you see the number of cores that goes from 1 to 262,000. And the problem is growing in the same proportions. So you go from 2 time steps to 524,000 time steps. So the degrees of freedom is also growing proportionally to an enormous amount of degrees of freedom. And this iterative method, this space-time multigrid method, it needs 7 iterations to solve the problem. It doesn't change at all. And the solution time is 30 seconds to solve the problem. And this is an interesting algorithm because it's not much slower compared to forward substitution, already just using 1 processor. And if you use 2 processors, then you're already faster. So there is no payment for the fact that this is a time-dependent problem. This algorithm is immediately faster as soon as you parallelize it than forward substitution. So that's why there is a column with forward substitution here. Similar result you also get when you do a strong scaling experiment. So you take a huge problem and you double the number of processors and you want to divide the time in half every time. The algorithm still has 7 iterations, does not depend on the parallelization. And you see the time is divided by 2, and it's still divided by 2 up to the last step. So this is an algorithm that has extremely good scaling properties for such time-dependent parabolic problems. But unfortunately, it does not work at all for hyperbolic problems. And this we saw in the implementation, and we also saw it in the analysis. And one should probably have published this negative result for hyperbolic problems, because it's important to know that this is an algorithm type that really needs the parabolic nature of this block matrix system. So why does that not work for a hyperbolic problem? What is needed for a parallel in time method to work? For this, we look again at the block system and at one line. Here is one line of this block system. You see it's a recurrence relation. So when can we solve this problem parallel in time? There are 2 things that would be needed to make this successful. One thing that can make this successful is if uj does not depend too much on the u's before j, and also not too much on the source terms before j. If this is the case, we can solve this equation sometime in the middle of the time domain, and we get a good approximation. Another way that it can work is if the algorithm has a cheap way to propagate important information that has to come from earlier time steps. So one needs one of these 2 conditions to make an algorithm successful. And to illustrate this, I take again the heat equation and the transport equation on my 0, 1 domain. Now the heat equation would have 2 boundary conditions, a g left and a g right. And the recurrence relation calculates u from u0, u1, from u1, u2, and so on to uj. In the transport equation, it's very similar. We also have the interval 0, 1. We calculate from u0, u1, u2 up to uj. The transport equation is a bit special. It only has 1 boundary condition. If a is positive, then this boundary condition is on the left, and on the right, the solution is just leaving the domain. So let's look at the numerical example. I just impose an initial condition on this first example, and let's see if this is local. For the heat equation, we see the initial condition has a local influence and nothing survives later in time. This is very local in time. For the transport equation, it's a little less local, but it still looks very local in time. The initial condition is here and it just leaves the domain. So it does not affect anything later in the domain. This is a very local property. It's the first property that we would like to have. If we put a boundary condition, the heat equation with a boundary condition here, it has a very local influence on the solution. Nothing is influenced here later in time. So this is also very easy to parallelize. The transport equation is a bit less local, but it also leaves the domain here. So it also remains very local in time to calculate. If we put the source term, it's very similar. The source term remains local in the influence for the heat equation, and it also remains local for the transport equation. So these two equations one should be able to solve very well with a time parallel method, because the influence of early parts of the solution do not have a great impact on parts later in the solution. So is the transport equation as a hyperbolic test problem a good problem? If we look at the transport equation again with the initial condition, this solution leaves the domain and it's local. But in a real true hyperbolic problem, you will have reflections that come back. For example, if this was a second order wave equation, this would come back here, and then it would go back here, and it would go back here. It would be much less local. And the trick one can use to make this into a viable test problem for PinT algorithms is to put periodic boundary conditions. So now suddenly it's less local. You see the solution is periodically transported, but we see immediately another problem of this hyperbolic test problem, which is the transport equation. I used the discretization which I presented, the backward Euler centered discretization, to calculate this. And you see, this actually looks more like a diffusion equation. The signal is getting lost. The true solution would really just be transported, no loss. So you can be fooled when you run your PinT algorithm on a transport equation if it's discretized like this, because in reality, you solve a diffusive problem. So the transport equation is a delicate equation to use as a test problem. If you want to use it as a test problem, you need periodic boundary conditions, and you need to discretize it such that there is accuracy left in your solution towards the end. This is even worse if you change the frequency content of your solution. Here I took a 1 sine wave. If I take a higher frequency component, there is much less left in the discretization scheme that I used. Whereas the real solution, it looks like this. So as a summary of this introductory part, the most important thing for testing PinT algorithms is to be very careful when you choose your test problem. For a parabolic problem, this recurrence relation here, it tends to forget a lot of information, and therefore you can solve a parabolic problem much more easily with a time parallel algorithm than a not parabolic one. These are a class of test problems where time parallelization has a good chance to work. This is why Martin Neumüller's algorithm, multi-grid algorithm, works so well on this type of problem. What do we know about the spectrum? The spectrum that indicates if it's going to work or not is in the K matrix. The eigenvalues of the K matrix in the parabolic case is just a 1 over delta t minus a Laplacian. The eigenfunctions of an Laplacian are the exponential functions. So if you take two derivatives of the exponential function, you get again the exponential function, and you just get a psi squared that comes out. So the eigenvalues are going to be positive. So in this case, if the kj have positive eigenvalues, you have this type of a problem, and time parallelization has a good chance to work. Now in the hyperbolic case, we can also look at the spectrum of the kj blocks. And if you look at the spectrum of the kj blocks, there was a 1 derivative here. The eigenfunctions of 1 derivative are still exponentials. You get an ik. So here the eigenvalues are going to be in the complex plane. This part is on the imaginary axis. So such type of problems have this type of behavior. And this cannot be assumed that the effect is local in time. So for such problems, you need another mechanism to make them work if you want to solve them in a time parallel fashian. This is a moment where I could pause for questions if there are any, before I will start to explain the para algorithms. So if there's any question in the chat, please let me know.
Yes, there is one that just came up. Ivan Oselditz asks if he just has a black box ODE, he doesn't come from a discretization from a PDE. How can he find out if it's parabolic or hyperbolic?
Then the first thing I would do, I would take this KJ matrix and calculate its eigenvalues. If they lie on the real axis, if they're positive, then it's this type of behavior. If they go way out into the complex plane, then you have to be very careful with your PinT algorithm. So this is what I would do. I would just take my problem and take my KJ and calculate its eigenvalues. I think this is a good indicator to tell you what type of algorithm can work.
Oh, okay, thank you. There's a bit more technical question. I just read it out. By looking to matrix A, can we have some kind of condition on the matrices KJ or MJ so that the symmetric part of A becomes a semi-definite matrix? Is that?
So that's a technical question. That's about the matrix,
The matrices
the space-time matrix, huh?
Yeah.
It's about this one. So the question is, what's the question?
By looking at the matrix A, can we have some kind of condition on KJ or MJ so that the symmetric part of A becomes a semi-definite matrix? It's quite...
I don't quite know how to answer this question just on the spot.
Let's take this.
I think I would need to talk to the person who asked the question.
Yes, we
can try this later.
Yeah. Yes.
Okay.
There's one more question by Howard Ellman that I'd like to read out.
Yes.
Aren't there stability issues associated with the implicit treatment of the hyperbolic problem independent of the parallelization?
The implicit treatment is actually quite good for the stability. It does not put you a time step constraint, but it's a good question because usually you would want to go explicit for a hyperbolic problem, at least for certain hyperbolic problems, you would prefer to go explicit. But here in my two model problems, I just chose implicit discretizations to have the same looking matrices. That's a good point.
Okay, I'll let you carry on and
okay.
Thank you very much.
So now I will explain the three algorithms I want to explain in my talk. And the first algorithm is the Parareal algorithm. And I will explain it purely at the linear algebra level using this all-at-once system in space-time. This first interpretation of Parareal I learned from Daniel Ruprecht in this linear algebra setting. The algorithm itself was invented by Lyons, Maday, and Turinici in 2001 at the PD level, so no matrices. But if I take my all-at-once space-time system, I just remove the right-hand side for the moment, so I don't have a source term here to make the writing simple. And I also remove the index j because for my two model problems, this j was actually not needed. All the k's were the same and all the m's were the same as well. So the basic idea to get to the Parareal algorithm is to just do a cyclic reduction step by eliminating, let's say, every second unknown vector. So if I want to eliminate U2 from this system, I can calculate the Schur complement. So in the new system, I only have U1 and U3. And you can see the U2 has been eliminated. And what you see appearing here is just 2 time steps, because you have to do 2 time steps to go from U1 to U3. So you have a 1 solve, which was doing the 1 time step that you eliminated, and you apply again the m to it to get to the second one. And you do this with every second unknown. So you get a new system which is smaller. It's a cyclic reduction step. It's smaller, it only has every second unknown, and it might have uj or uj minus 1, depending on if it was even or odd. You could also eliminate more time points. So suppose we eliminate all time points and keep only every mth time point. Then the system becomes much, much smaller. It still is of the same form. You have the k's on the diagonal, But here now we have what I call F, and F is a matrix which applies the time step m times. So we just go over m steps here. And in general, we use uppercase letters now for the unknowns, because in the Parareal algorithm, this uppercase means we're at the coarse time points now. Every fine time points have been eliminated. Now, what is the Parareal algorithm? The Parareal algorithm is a very simple stationary iteration, which I wrote here. The UK plus 1 is the old UK plus a B inverse times F tilde minus A tilde UK, where A tilde is this new, much smaller matrix. F tilde is the smaller right-hand side. And B is a preconditioner. And it's a preconditioner that looks like the matrix A tilde, but it has a coarse time step per G here. So instead of doing M fine time steps, it does maybe one coarse Euler step or two coarse Euler steps, and that's it. That's the Parareal algorithm. So it's very easy to remember at the linear algebra level. It's just doing cyclic reduction to your system and then build a preconditioner by approximating the many steps which you eliminated by one step or maybe two steps. That's the Parareal algorithm. What is known about the Parareal algorithm? It's known that it converges in at most n iterations if you have n coarse time points. So this matrix iteration is nilpotent. This is a very interesting property of this iteration matrix. It's also known that the convergence of this method has a superlinear upper bound. This was proved by me and Stefan in an early paper. And this upper bound looks very different for the heat equation or the transport equation. For the heat equation, it contracts very rapidly. If you have a hard time to read the scale, here it goes to 10 to the minus 36. And you see it's superlinear, the contraction. For the transport equation, the bound is also superlinear, but it has the typical shape that you have for highly non-normal matrices in an iteration. You first go up, go up, go up, go up, and then you come down and down and down. And you come only down once you get to the nilpotent n. The different colors are different numbers of coarse time intervals. And you can see you come down at the point where the n will indicate finite step convergence. There is also a linear convergence estimate, which holds for long time intervals for the heat equation, not for the transport equation. So if you look at the numerical experiment, then here on the left, I have a heat equation, and on the right, I have a transport equation. And for the heat equation, there are two bounds on the convergence. The red bound is the superlinear bound. The cyan bound is the linear bound. And the dashed line is the actual error measured. And you can see it goes first linearly, and then it transitions into a superlinear regime, and then it hits the finite step convergence. So in this graph, you see all three properties that this algorithm has. On the right, for the transport equation, there is no linear convergence bound, but there is a superlinear convergence bound. And the algorithm itself, for this example, it just stagnates, 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 and then it has a finite step convergence. There are further known results. The algorithm is also defined for nonlinear problems. It converges also superlinearly for nonlinear problems. One can show that it's a geometric multigrid method. And there is a very important generalization that has generated a lot of new information and algorithmic techniques, which is called mgrid. The first variant came from Friedhoff, Falgout, Kolev, McLaughlin, and Schroeder in 2013. And there are two main new components that are added in mgrid compared to Parareal. Parareal, as I showed you, is a two-level method. mgrid is a multi-level method. So it's a multi-level extension of the Parareal algorithm. And in addition, they introduced a FCF smoothing procedure, which one can show corresponds at the Parareal level to overlapping intervals in time. And there is a very good software package that you can just download and use called XBraid. Now I'd like to show two results that are about the transport equation, which are very recent. This is work by Lunet, who is actually currently in my group. We revisited the transport equation because in the literature you can find results that show that this parareal type algorithms also work for the transport equation. And we tried to understand why that is possible. So here you see an experiment where the iteration number k is on the x-axis and the error is on the y-axis. And we solve the transport equation with a Parareal algorithm. We use a backward Euler in time and a centered 6th-order finite difference stencil in space. And you can see this method does converge. The three curves correspond to three different resolutions. The blue curve has 1,000 points in space. The orange curve has 2,000 and the green curve has 4,000. So the more you refine, the faster it actually functions. So here it seems it works rather well. If you look at the accuracy of the solution, the accuracy for the 1,000-point grid is 2 times 10 to the minus 1. For 2,000, it's 8 times 10 to the minus 2. And for 4,000, it's 4 times 10 to the minus 2. So the accuracy is not great. The accuracy is about here on the graph, here. This is the accuracy of the solution. But we see something else that happens in this experiment. Suddenly, all graphs seem to join another convergence curve, which is this one. And this convergence curve, we now understand, and we can even predict it. It's this, following this line, which is dashed in gray here. Now, this was a solution which is just one low frequency mode. It's a low frequency sine wave. So we have 1,000 points per wavelength, 2,000 points per wavelength, and 4,000 points per wavelength, which is excessive as a resolution. The reason why we don't get any accuracy is the backward Euler scheme here. It's diffusive. So let's take a better scheme. Here is a better scheme. It's an S-Dirk3 time scheme. The spatial scheme is the same. The algorithm still seems to converge. It has a more pronounced bump. The meshes are all the same. But especially you see that these gray lines here, on which all the other curves join, is now much more violent. So what is this gray curve here? This gray curve is a frequency which does not exist in our initial condition, which is generated by round-off error, like when you calculate eigenvectors and eigenvalues with the power method. And this is the one that dominates the convergence behavior of the method. And you see it has the same shape that I've shown you before in the analytic estimate. So if in the initial condition we had a mode with this frequency, then this curve would start here and we would have exactly the same plot that I've shown you before from the convergence estimate for advection equations. So when testing algorithms, it's very important to test on all frequencies, start with a random initial guess, and to verify if these convergence curves actually have some accuracy. In this case, we have accuracy. The green one, the solution is 10 to the minus 9, but cannot be calculated with this algorithm, except once we've iterated our 50 steps for the 50 time points that we have. So that's an important comment for Parareal. The next algorithm I would like to explain is ParaExp. This is an algorithm that Stefan Guttel developed when he was a postdoc here in Geneva. And the idea is very simple. We take again our all-at-one system, and instead of solving this system, we solve two systems. We solve two problems. One problem has only the right-hand side source terms f, and the other problem has only the initial condition u and no right-hand side. Now, by linearity, if we solve these two problems, then we can just sum them and we get the solution of the original problem. So why could this be interesting? the key observation is that one of these problems is much, much cheaper than the other one. And it's the second problem. The second problem, it would not be a good idea to do time stepping on this problem because it's basically just a matrix exponential. So instead of doing time stepping on this problem, it's much better to approximate the matrix exponential for this problem. Whereas this one you solve by time stepping. So how do you get a parallel algorithm from this? We partition the all-at-once system, for example, into two systems for two processors. And then we first solve in parallel two problems that only have the F right-hand side. The first problem, which is the upper block, and the second problem, which is the lower block. So in the V's, we have now all the information of the right-hand side. So the only information missing is the initial condition and this initial condition, which is produced by the first solve for the second solve. So now we solve two W problems. One W problem with the initial condition and one W problem from the middle on, which takes the value which was just calculated before with the right-hand side. So note that the two V problems and the two W problems can be computed in parallel. And the most important point is the W problems should not be calculated like it's written here as time stepping. Especially because this first W problem, it goes over the whole time interval. This is a longer W problem than this one. This only goes over the second half. So how do you calculate these problems? These W problems are solved by using good approximations of the matrix exponential. And they're projection-based methods. They're expansion-based methods. And you don't need to implement those. There is a very good toolbox that Stefan Guttel with collaborators has been developing since 2013. So you should not try to approximate the W problems with some code that you come up yourself. It's best to take this toolbox to evaluate them. Now, an interesting property of ParaExp is it's a direct method. There is no iteration. It just solves the problem in a parallel manner in space-time by two steps, solving V problems and solving W problems. And in my example, I had two, but you can have 10, 100, 1,000. There's also a nonlinear variant of ParaExp. And I show an example for a wave equation, which goes back to Stefan Guttel as well. So here is a second order wave equation. The wave speed is alpha. The right-hand side source has a frequency f. We have boundary conditions on both sides. Initial condition is 0. And you can see that if we calculate this solution in a serial manner, it takes a certain amount of time to get to a certain error level for different values of the wave speed and different values of the frequency. If we use the ParaExp algorithm, there are two different times. The T1 is for the V problems. These are the ones that do the source term. These are the ones that do time stepping. And for the V problems, which are the ones that do the matrix exponential. And even though those go over much longer time intervals, you see they're way cheaper than the ones that incorporate the right-hand side. So you get a very good efficiency for this hyperbolic problem. So what's the key ingredient that makes this work? It's the matrix exponential, which transports important information over long distances. That's why it can work for a hyperbolic problem. Now I'd like to get to the last family. It's the ParaDiag family of algorithms. And you start again with this all-at-once system. And now I reintroduce the index on the matrices because I want to use a different time step for each integration step. So the case I have an index j. Kj is still defined as before. Mj is still defined as before. And L, it is either the discretized Laplacian or the discretized transport term. So this is the system like I had it before, but I have now an arbitrary time step for each time integration step. And what one does for ParaDiag, one separates the time discretization from the spatial discretization. So this is the same system as I have here. I just put the M's again together and the L alone. And so you see that this system has a Kronecker structure. I can write this as B cron I, where I is an identity matrix of the spatial size, and an IT cron L, where IT is a matrix identity, is the size of the number of time steps. This is this system. Now, to solve this system with ParaDiag, there is an idea of Maday and Ronquist that says if all these time steps are different in the B matrix, you see this is really the backward Euler with different time steps. If all these Tj, delta Tj are different, we can diagonalize B. This bidiagonal matrix can be diagonalized. The eigenvalues, you can see they are on the diagonal. So they can be diagonalized. And this means we can factor the block bidiagonal problem in this form. So there is a change of basis, then there is a green block diagonal part, and then there is again a change of basis in the blue part. So like if this was an LU decomposition, you can solve this problem now doing 3 steps. You first have to solve with this part for a new unknown V, which is this one. Then this becomes the right-hand side, and you have to solve the green part. And the key step in this algorithm is all these green ones, which are the ones that contain your spatial operator, they can now be done in parallel. It's a block diagonal system. So instead of time stepping one Laplacian after the other, you do all the Laplacians at once in parallel. And then you have the last step which you need to solve, putting again what you just calculated as a right-hand side. So it's a very simple idea, but it needs that these time steps here are all different. So what is known about this ParaDiag-I type algorithm? It's again a direct solver like ParaExp. There are no iterations. One has to be extremely careful to balance truncation error and round-off error, because when you diagonalize a matrix like this, it almost looks like a Jordan block. If all these time steps are the same, it actually is a Jordan block, so you cannot diagonalize it. So you can imagine that there is a very, very delicate estimate that you need to not destroy this method by round-off error. And for a geometrically stretched time grid, which is using from the old time step a 1 plus epsilon multiplication to get to a new time step, so all these time steps are linked, one can actually analyze and one could determine what the best choice for epsilon is to balance truncation and round-off error. This method works well for parabolic and hyperbolic problems, but the analysis shows that you cannot do an arbitrary number of time steps. You can do about 20 time steps. If you want to do more than 20 time steps, even if you balance this in the best possible way, round-off error in double precision will destroy the algorithm. We had a very interesting suggestion by Nick Hayam to look at random time steps, which Bart and I both tried, and somehow this seems to be really a hard bound. You cannot overcome this. It's a fundamental problem of ParaDiag-I algorithms. There is also a nonlinear variant. Here is an example of an industrial problem. It's the elasticity equations. There is a clamped plate, clamped on 4 points, and there is a load here. And the algorithm scales extremely well in the range where it's designed to use. So in this plot, we see time on the y-axis, and then we see one processor, the sequential execution, 2 processors in parallel, 4 processors in parallel, 8 processors in parallel, 16 processors in parallel, and 32 we cannot do because the algorithm just doesn't work anymore. It's destroyed by round-off error. And the bulk cost is the LU solves of this spatial operator. And you see it scales very well. It's divided by 2. You also have the overhead, which you have in all these implementations, the factorizations, which at some point will take over, so you cannot parallelize arbitrarily. So you want this matrix P that you can diagonalize also if you have equal time steps, because that's the problem in this algorithm. If you want to have time steps that are very close, you cannot diagonalize this matrix. So a key idea was invented by two different teams independently, and it's to put a term here in the time step matrix. So now I take the same time steps and I just put a minus alpha over delta t here. If alpha is 1, this is a circulant matrix, so I can diagonalize it directly by Fourier. If alpha is not 1, it's an alpha circulant matrix, I can still diagonalize it with Fourier techniques. But now we solve the wrong problem, because it's not B tilde the time stepping. The real time stepping doesn't have this term. So we need to use this as a preconditioner. So we have the original time stepping matrix written in Kronecker form, and we have the new time stepping matrix also written in Kronecker form, and we just do a stationary iteration. This was discovered in the group of Andy Watton with alpha equals 1, and they directly posed this as a preconditioner for GMS in 2018. And it was discovered at the PD level by Shulin Wu, who introduced the alpha. And at the PD level, this looks like a head-tail coupling condition, because somehow your initial condition is coupled to your tail end value of the problem. So it's called a head-tail coupling condition. What do we know about ParaDiag-II families? There is a very interesting analysis done by Andy Watton and collaborators. There are spectral estimates for the heat equation case. There is also a very elegant symmetrization of the method, so you can use a min-res algorithm. All is done for alpha equals 1. Then with the other values of alpha, there are convergence factor estimates at the PD level. This is work of Shulin Wu. We have for backward Euler a contraction of this algorithm, which is a waveform relaxation algorithm in the PDE setting. And if you have trapezoidal rule, you have this type of contraction. So you see, if you choose alpha small, this contracts extremely fast. And in backward Euler, you benefit a little bit from the diffusion part if L has a diffusion in it, otherwise not. One can also use this ParaDiag-II algorithm to approximate G in Parareal. And then you can use the same mesh also in space-time for G and F. So you can't solve hyperbolic problems because there's no dispersion problem anymore. There is a software repository which is prepared by Shulin Wu, which will go online soon. There is also a nonlinear variant of this algorithm. I just want to show you how it works for a advection diffusion equation with a very, very strong advection term. So diffusion is very small. This is the initial guess. It's random, like I mentioned. It's important to test with random initial guess. In the first iteration, you immediately see the transport term. Space is here on the left, time is on the right. These calculations were done by Shulin Wu. And this is the second iteration. You see we have a very sharp signal. And here we are with a diffusivity, which is very, very small. So it's basically a transport equation. The algorithm is robust when you make the diffusivity small. So if you go from a real diffusive problem to a almost pure transport problem, convergence is very fast. You go from 10 to the 1 to 10 to the minus 12 in 5 or 6 iterations. Alpha was chosen 10 to the minus 2. It's also robust in mesh refinement because you actually solve the correct problem on the correct mesh. The only approximation is in this time periodic head-tail condition. So to conclude, I started by 2 model problems which I think are important for understanding these algorithms, the parabolic heat equation and the hyperbolic transport equation. And I've shown you that the parareal type methods are greatly affected by the difference of these two, whereas ParaExp and ParaDiag are much less affected by this because they have a mechanism to propagate over long distance, also fine information in the solution. There were 2 more algorithms I would have liked to explain, but I just mentioned them now in the conclusion. There is the ParaOpt family of algorithms. These are algorithms that are for solving optimal control or PD constraint optimization problems with time-dependent constraints. There is a first algorithm that was proposed by Barker and Stahl, which is basically applying an additive Schwartz method to the coupled forward-backward problem, which we studied very carefully with Felix Kwok, and we showed that it's actually an optimized Schwartz method. You can also apply this parareal idea and course correction to the optimality system, and not just solving the forward or backward problem in parallel, but by really devising a new algorithm that solves the coupled problem with parareal technology. And there is the ParaDiag variant developed by Shulin Wu again, that solves the optimality system by diagonalization, again, very successfully for the wave equation. There is also the ParaStieltjes algorithm. I want to mention it for two reasons. One reason is that we've heard about the Stieltjes procedure in the last talk by Nick Trefethen. The Stieltjes procedure is a very nice recursive procedure. And if you hear recursive procedure, you should immediately think about the time stepping procedure that we've seen in the all-at-once system. So what we try to do there is we try to devise an algorithm that calculates the Stieltjes recurrence procedure in parallel to compute Gauss quadrature rules in parallel. So this is not a time-dependent problem anymore, but the PinT algorithm can be useful for this type of problem. And another very nice example I like a lot is the mGrid algorithm used in machine learning, which was presented by Jakob Schröder in 2017, where again, machine learning has no time-dependent problem, but this technology can be used for problems that are not coming from a time-dependent application. So I'd like to close with this, and I'm ready for questions.
Okay, thank you very much for this great talk. There are a couple of questions already on Zoom, which I'm just going to ask. So one was on the ParaDiag. So when you do when you solve the sequence of linear systems, where you alternate, there was one question about what happens if you solve inexactly. Does this have any effect?
This has a similar effect that you also have if you did it inexactly in the time-dependent case, but the errors are not going to accumulate. They're not going to accumulate in the same way because you solve the systems all in parallel and then you sum the errors. But I've never tried this myself. Approximately, I would have to do it myself to be more precise.
Mm-hmm. Okay, and another question by Cecilia Pagliantanini, or probably, hopefully not pronounced wrong. For the parallel and time algorithms, are they structure preserving in any sense? So are they providing any geometric temporal integrator?
That's a great question. There has been a tremendous effort to try to devise a structure preserving parareal algorithm. And we finally proved with Ernst that it's not possible in the context of parareal. The structure of parareal does not allow you to have a structure preserving iterate. There is a different approach, which is really not like a parareal algorithm anymore, that generates structure preservation. That was by Guillaume Ball, but it's an algorithm which is difficult to use. It needs a lot of accurate interpolations. So in my experience, the parareal type algorithms will not be structure preserving. There has been efforts to be energy preserving. They're not. For the other algorithms, it depends what your underlying algorithm gives you. For example, for the direct methods, they provide the solution that you would have gotten also from the underlying sequential solve.
Okay, thank you. Hopefully that answers the question. So there's another one by Ivan Oseldis. So for the parallel algorithm, you have this coarse fine grid solvers methods. Do you have those for the ParaDiag and the ParaExp as well?
In the ParaDiag and ParaExp, there is everything is running on the original mesh. So there is no coarsening. These are really solving on the same structure. They're not iterative in the sense of ParaExp and ParaDiag-I. ParaDiag-II is iterative. It doesn't have a coarse component so far. Maybe one should think about a coarse component. Yeah, for the moment, they don't have a coarse component.
Okay, thanks. And the final one before I go to Stefan on YouTube is by Volker Mehrmann. He's suggesting, would it not be faster to just use model reduction like POD or shifted POD for hyperbolic problems and then have a smaller problem?
This is an interesting suggestion. Yes, there are actually There are Parareal variants that uses the coarse integrator, a model order reduction approach. So it becomes much, much cheaper, and it still retains the essential features. I think this is a good suggestion, yeah. I think this should be, can be investigated and can be effectively used. Yeah.
Yeah, I think probably Volker has done some work on this already. Over to you, Stefan, on YouTube. Do you have any questions?
Yes, I have a couple of questions. One is by Amon. So he is referring, or he or she, in fact, referring to this hump behavior of the parareal iterates for early iterations in the transport equation. Mm-hmm. And the question is there a specific frequency that dominates this hump?
Yes, and we calculated where it is depending on the discretization which is used. So we know exactly where the hump comes up, and you saw it's not depending on the mesh size. So it's not the highest most frequency. It's an intermediate frequency which is dominating the convergence behavior.
And this frequency can be calculated?
Yes, it's calculated. If you look in the manuscript with Stefan van der Walle, we calculated the frequency for several discretizations, and also in the lecture notes that I'm trying to finalize for a book about time parallelization. I calculate directly where the hump is depending on the method. Yeah.
Mm-hmm. Cleve Muller asks whether there are Parareal algorithms for tensors and neural nets.
That's a good question. There is this M-grid variant that has been used for machine learning by Jakob Schröder. And the way he explains it, he says, when you have a deep neural network, and when you do the learning, then you have to go forward and backward through these layers of the deep neural net. And this process he interprets as a recurrence relation. And so he can apply this M-grid algorithm, which is the Parareal algorithm, with additional features. So I think yes, this algorithm can be used in the context of machine learning. Yes.
Giancarlo Antonucci asks, well, you have mentioned that ParaDiag-II can be included within Newton's method for nonlinear problems.
Yes.
Is this already published work?
Yes.
Are there some references?
I think there is a reference which is in revision now that should contain this, or maybe Shulin already has a paper on this. So this is stuff which is fairly recent, but it's very clever. Yeah, it's very clever.
Okay, thanks, Martin. There are no more questions on Zoom.
Yes.
There was a comment by Jens Zemke on that there is work on Parareal and machine learning. So he sent a link. So we.
Oh, excellent! Wow.
We can. You see the chat, so you can see the.
Yes. I'll look. Yes. Yeah. Very good.
But there's no more questions as far as I can see. So thank you very much again.
Okay, great. Thank you so much.
I hand over to Jörg.
Can I just say one more thing?
Yeah, go ahead.
For people who are interested in time parallelization, currently there is the 9th time parallel time integration workshop running. It's running electronically. It's based in Michigan, and the talks are just from 5 to 7. So if you look on the internet, PinT 2020 Michigan, then you find links, and there is going to be a funny talk later this afternoon about dozens of ways how you can fool other people with your parallel and time results, and maybe even yourself. So there should be a fun talk later this afternoon as well, if you're interested in.
Okay, so if it starts at 5, it's perfect timing, right?
It's possible to do, yeah.
Yeah. Okay. Thanks.
Okay, thank you very much, Martin, for this very nice presentation. To everybody for the lively discussion. And let me just pull up our upcoming talks. So our seminar series will continue next week with a talk by Mark Embry. And as you can see, we have a great lineup of speakers after that also. We will go until July 22nd, and then there will be a summer break. And you can see how it will continue after that on the website. So until next week, bye-bye and have a good day.